In this video, we're going to begin discussing the general linear model. We've been focusing on the simple linear regression model where we have one predictor variable and one response. In the general linear model, we can actually begin to model a response as a linear combination of several predictor variables. And so it might look something like this. Maybe you can predict a response variable. The ith response is modeled as a constant, some number, plus some number times a variable, plus some other number times a variable, plus and so on and so on. We'll use p here to denote the number of regression parameters, okay? So beta 0, beta 1, up to beta p minus 1, there are p betas, okay? P betas. Some books, just to warn you, will use p to denote the number of predictor variables. Here, the number of predictor variables is p minus 1, but so we're using p for parameter, okay? P is the number of parameters. Okay, so it looks a lot like the simple linear regression model. Of course, we're adding our our random errors here at the end. The only difference is that we have more predictor variables or more explanatory variables allowed in our model. We can write this using matrices where our vector of responses, 1, 2, 3, 4, n responses. Okay, if we make n responses, it's going to be a vector where it's going to be our x vector, our data matrix, if you will be a column of ones along with all of our observations on the x variables. Okay. Each column here corresponds to another variable in the model, and each row then, for example, if I look at this element right here, this is the second observation on the first variable. Okay, this is the nth observation on the first variable. Okay, this is the nth observation made on the second variable. Our beta vector here is our vector of coefficients that we'd like to know. We're using betas here because we're thinking in terms of a theoretical model, and these are our random error terms. And in fact, you should see that if I do matrix multiplication here, for example, if I take the first row of the x matrix and dot it with the betas, I get 1 times beta naught plus x11 times beta 1 plus x12 times beta 2 and so forth and so on, plus this guy right here times this last beta here, which is this last term up here, of course, if I was equal to n, and then plus at first epsilon value. Okay, all right. So now, these predictor variables may or may not be independent. They could be highly correlated or not so much. We'll investigate what happens if the predictor variables are highly correlated later on when we get to multi-code linearity. These error terms are still assumed to be independent normal random variables with mean 0 and variance sigma squared. We're going to investigate this graphically here in a couple minutes. It turns out, though, one thing that we'll see is that we no longer insist on the mean response being a linear function of the predictor variables. Turns out the reason we call this the general linear model is that it's linear. The model is linear in the betas. Okay, let's check out a couple of different examples. We might model the first year GPA for a student as a function of SAT score and high school GPA. Okay, SAT score, high school GPA, multiply those numbers by constants, add another constant, slap on a random error term, and boom, there you go. In this case, if I remove this random error term, all this stuff right here is just the equation of a plane, right? Y is a function of these two variables, x1 and x2. However, check this out. What if instead, what if this xi2, what if this variable here, what if this guy was actually the same as this variable but cubed? Then this response is really a function of one variable, right? It's it's a constant plus a constant times x, you can think of, plus another constant times x cubed. So it'd be a cubic model. Okay, you've graphed cubic equations. Y equals, say, 5 plus 2x minus 6x cubed, right? Okay, you can also introduce interaction terms into your model, where maybe you have something like y equals a constant plus beta 1 times an x plus beta 2 times another x plus beta 3 times another x plus beta 4 times another x. But maybe this variable here is really the product of the first two variables, and maybe this one here is the square of this one. Okay, that's perfectly okay. So in this case, we can actually build models that are not flat and planar anymore. They could certainly have some curvature. But the deal here is, remember, we call this the general linear model because the model is linear in the betas. That is, if you were to look at this model as say it's fixed and the x values, and then allow the betas to vary, it's a linear combination of the beta values. Okay, so that's why it's called the general linear model. If I look at this vector x times beta, this contains all the conditional expected values of the y's given the x's. Okay, because if I condition on the actual values of the x's and try to write down an expression for the expectation of the ith y value, if I just substitute in there for the ith y value, it's beta naught plus the sum of the betas times the x's plus that random error term. Of course, the sum of the expected value, the sum is the sum of the expectations, so I can write it thusly. All right, the conditional expectation of the beta naught given all these x's plus the sum of the conditional expectations of those guys. All right, you'll notice that when I make this transition to from here to there, I've included this, right, the expected value of that random error term. This expectation is 0 by assumption, right? This expectation is 0 because these epsilons are still, we're assuming they're normals with mean 0, and so the mean is 0 here, and then expected value of beta naught given all this stuff is just beta naught. Beta naught is not a random variable. The expected value of these guys given these, there's no randomness in here. If you're given the x values, it's just all this stuff. Okay. In matrix notation, this is the same thing as writing this. Okay. Given the data matrix x, the expected value of the y values is just the data matrix x times the vector of the betas. Okay. So let's check all this stuff out. Let's see what's going on here visually. I think it's really important to be able to check things out visually. So I'm going to use R. I'm going to use a library called the RGL library. It's a graphics library. And so let's see what's going on here. I'm going to start with sort of a simulation, okay? So okay, there we go. I'm going to generate 700, why 700? Just because 700 random uniforms between -5 and 5. Okay, and put them in X. Okay, you can make a histogram of that stuff, by the way, if you go like that. And yeah, sure enough, it looks sort of uniform across there. The bars have quasi-uniform heights. By the way, when you do this, your graph will look different from mine because my simulation is probably starting with a different seed. Okay, or it might look exactly the same. I have no idea. Okay. Similarly, I'm going to also generate some 700 uniform random variables between -5 and 5 and store those in Y. Okay, so if I plot say Y versus X, I should see just a bunch of points in a square that's sort of randomly distributed there. Let's see. Whoops, where did they go? There they are. Okay, yeah, that's exactly what about the kind of thing I would expect. Okay, Now let's get some z values. I'm going to call this z true, okay, because I'm actually going to build a function called z true out of those that depends on the x values and the y values. I'm also going to get some random error terms, okay. And by assumption, our errors are normally distributed random variables. I'm going to do 700 of them, one for each one of these points, with mean 0 and standard deviation 1. Okay, so I'm going to now I'll say z true here is this is a function of x and y. Okay, so I can actually plot that and get some kind of a surface. You can see that it's going to be some kind of quadratic, right? Because it's got squared terms in it. We'll plot that in a minute. But I also want to what if I build a fuzzy model here and of some data. I'll call it z data 0 for 0 error. Okay. I'll let the idea here is I'm going to let that be let these z values, this guy be our actual z values plus no error. Now what if I multiply those errors by 10 and added? I bet you I'd see something sort of fuzzy there. What if I multiply those errors by 70 and add? I bet we'll see something even fuzzier. By fuzzy, you'll see exactly what I mean, and by C, I mean we'll make a graph and we'll see it. Okay, let's make a linear model of the z variable when we have no errors there, and I'm going to include the squared terms. Okay, this is how you do that in R. As usual, I typically call my output as something like out. I'm going to call this out 0 for because I'm going to try to make a linear model for my z values with no error versus this is how you get your squared terms in there. Okay, I of x squared y and plus I of y squared, like that. Okay, and I'm going to store my fits for this model in fits 0. Okay, and I'm going to do the same thing then for when I have errors of standard deviation 10 and standard deviation 70. Okay. Now I'm going to create a matrix. So what is this? Okay, and I'm going to use this matrix to make some plots. Okay, you'll see exactly what this does in just a minute. And it turns out actually I'm going to need to take the transpose of that. So mat will actually be, that's short for matrix, not short for me, it's short for matrix. It's the transpose of this matrix. So now if I do mat, you'll see that it's taken the transpose. And this is this command, this layout 3D command, is a lot like that par mfrow stuff that you did when you're making plots in 2 dimensions. Here's my little plot window. What I'm about to do is make some plots in three dimensions. Now, so here's what I'm going to do. I'm going to say plot 3D x, y, and z data 0. Okay, so this is when we have 0 error, and I'm going to color the points red. Pink. Oh, look at that. Okay. Here's what's really cool about this, folks. If I drag this with my mouse, you can see it. You can spin it around. Now, you can see exactly what's going on here. Well, hopefully. Oh, and guess what? If you have a mouse, you can zoom in or zoom out on it by scrolling. Excuse me. This is sort of a perfect model. It's sort of a functional model. There's no error there. The z values are going up and down this way. The x and y values are all down in this plane. So you can see how this is definitely a paraboloid kind of deal going. It's got concavity. It's concave downward. Okay, I'm going to put this over here for a second. And then if I do this next 3D command, that's similar to the Windows command, or to the, but it says, it essentially says move to the next point in that matrix that you created and make a new plot. Now I'm going to plot 3D XYZ Z data 10 and color it red. Okay, so this is sort of my perfect model with no errors. Now in this model you can see it is in fact a little fuzzy, right? Can you see that? How the Z values are off in the up-down direction just a little bit from this perfect paraboloid sort of structure there. It's a little fuzzier. It's not as perfect or smooth looking. Okay, I've done that by simulating some error terms. I'm going to move to the next square there, and I'm going to now I'm going to put the plot 3D stuff there where I'm plotting Z data 70. Make sure you get the 70 there. And then one incarnation of my notes I had a 60 there. It won't work if you don't use the right name for that variable. And now if I look at my plot, you can see yeah, look, this one is even fuzzier. It still has sort of that paraboloid shape, but you can see as I've increased the amount of those errors by just increasing the standard deviations, that they're sort of blowing off in the up and down and around, just up and down direction off of this perfect model. So that's okay. There we go. So now I'll move to the next place, and now what the next few lines of code will do is add titles. Okay, so I'm just going to do that real fast. I'm going to copy the next 6 lines of code, and you can see that I've added titles there. Here's my actual mean behavior. Here's some empirical. You can think of this as empirical data behavior, where the standard deviations of those normal error terms is 10, and here where the standard deviation is increased to 70. So now I will move to the next row down there. I'm going to plot some other things, and I'm just going to copy the next 6 lines, and you can see what I'm actually doing now is I'm gonna plot the fits from those linear models. Remember we actually ran these linear models up here and got the actual fits, right? So here they are. In the first case, it looks exactly like the original perfect model, right? And it should, because the error terms were actually all 0. In the second case here, it also looks pretty perfect, and in the third case, it also looks pretty perfect. In fact, these 4 all look the same, but they're not. These 2 are the same. This is a little bit different from these 2, and this one is a little bit different from these 2. Remember, this is the linear model that's associated with this fuzzy hairy stuff. Okay, this is a simulation of observed data based on this, that we've simulated based on this model, and introducing some random normal terms. These are our fits that arise from building the linear model estimate from these observations. This is also nice and smooth, but remember, these are the estimated fits that arise from building the linear model based on these observations. So these 3, while they look pretty much the same, they are in fact a little bit different, and we'll see that momentarily. Let me slap some titles on there. I'm going to get the next 5 lines of code there and drop those on. So now I've got model fits from the actual. These should be exactly the same, because the when the errors are 0, sum of squared errors is going to be 0, right? Again, these are the model fits when the standard deviation was 10 for those errors, and these are the model fits when the standard deviation of the errors was 70 Okay, yeah. So now to see what I'm talking about here is let's get the the do the summary. Get the do the summary of our linear models. You can see that. So for our sort of our perfect model, we see that um, our our coefficients of our model were -4 and -7, right? The -4 on the x and the -7 on the y, and the intercept was, I guess, 1 times 10 to the first. Okay, and these p-values were extremely small, and so you can see that in fact, yeah, these are the actual coefficients, right? If you look back in our code here, in fact, yeah, see, you see it right here. Z true, our actual model was 10 minus 4 times x squared minus 7 times y squared. Okay, but now look, if I look at the linear model output based on you know, when these are simulated data, right? If I build the linear model based on these data values, look at our estimates. They're a little off. Okay, -4.0373 and -7.04268, and our intercept coefficient is a little bit different. And in fact, then when I have a larger standard deviation, I can expect to have a little more variance in our actual model coefficients, right? So here's these finally are the intercept and slope coefficients for our linear model when our standard deviation was 70. Okay, it still looks nice and smooth. It looks nice and parabolic down here, but it's not situated in exactly the same place. Okay, these numbers are a little off. They're estimates. Okay, so I hope that sort of sheds some light on what's going on here, and also it'll be great to be able to make some really cool pictures like these. So we'll be using this RGL package from time to time.